Okay, so good evening, everyone. Welcome to today's webinar on FRP-coated steel rebars, a real solution of corrosion protection for concrete structures, by Dr. Xiang, who is a research assistant professor in the Department of Civil and Environmental Engineering at the Hong Kong Polytechnic University. Dr. Xiang conducts interdisciplinary research in the fields of materials science and structural engineering. His research interests include advanced construction materials, new material hybrid structures, and structural health monitoring technologies. He has contributed to more than 15 research projects and authored over 30 journal papers, 2 of which were recognized as ESI highly cited papers in Web of Science. So without further ado, please welcome Dr. Xiang.
Thank you, Christy. Thank you for coordinating today's seminar. Thanks Hong Kong IE and Department of Civil and Environmental Engineering of PolyU for providing this chance to deliver my report today. Before getting into my research topic, I would like to spend several minutes to briefly introduce our CEE department. Our department has been a leading university department in civil and environmental engineering today. We have now 26 scholars ranked the world's top 2% scientists as released by the Stanford University. We have 1 member of the Chinese Academy of Sciences, 1 fellow of the Australian Academy of Engineering and Technology, 1 fellow of Royal Academy of Engineering of UK, and we have 7 Changjiang scholars of Chinese Ministry of Education. Because of the attempts made by our outstanding scholars, CEE has received global recognition. Our civil and structural engineering was ranked 14 in the QS subject ranking last year, and our civil engineering was ranked 2 in the Shanghai Global Subject Ranking last year. Riding on the global recognition in the rankings, CE has performed very well in securing external research grants, including 4 theme-based research projects, each with a grant of over 30 million Hong Kong dollars. Apart from that, we have also secured other major research grants like Green Tech Fund, RGC Collaborative Research Fund, and also Research Impact Fund in different areas. CE department offers a wide range of programs in civil and environmental engineering. For undergraduates, we have a bachelor's degree in civil engineering and a bachelor's degree in environmental engineering and sustainable development. For top postgraduates, we have Master of Science in Civil Engineering and a Master of Science in Environmental Management and Engineering. Over these years, we have a number of outstanding alumni. For example, Professor Choi, the past president of Hong Kong IE, Mr. Ricky Wong, the current head of CEDD. In our department, we have excellent hardware base for our staff and students to do research, including 30 laboratories, 2 workshops, and 1 research center in Shenzhen. We have also been very active in promoting our social impact. Our supporting chronicles have established many social media channels for public to know more about our department, education programs, and some other informations. If you need to know more about them, you may access these QR codes and links to get these informations. So let's move on to the research topic today. Today, I will introduce a new technology for corrosion protection of concrete structures serving in marine and coastal environments like Hong Kong. It is called the FRP-coated steel rebar. My report today will be composed of these 5 parts. The first is the background of the research. The second is some knowledge about the fiber reinforced polymer composites, because it is a part of the technology I'm going to talk about today. The third is the FRP-coated steel rebar, the new technology, and then the concluding remarks and last acknowledgement. As you may know, corrosion of steel has been a major challenge for infrastructure construction, especially in marine and coastal areas like the Great Bay Area, Hong Kong, and other places. But you may not always know the exact number about the economic loss caused by steel corrosion. It is roughly estimated to be about 3% of the GDP population. For China, it was about 4 trillion Hong Kong dollars in 2022. For the United States, the number, according to the American Society of Civil Engineers, ASCE, they need about 46 trillion Hong Kong dollars for infrastructure maintenance from 2020 to 2029. In my spare time, I took many photos on my walk in Hong Kong. We can find that the corrosion state near all of us is really very serious. For example, here is the staircase in Whampoa. Here are some beams of the like Zhejiang Pier. There is a pier in that place. So this not only looks unattractive, but also a kind of dangerous for people walking along these facilities. Maybe every engineers like you and me will ask how to properly address the corrosion issue after knowing the above. In fact, history has told us the answer. We went first from living in lateral caves to coming out of these caves and build houses using natural materials such as mud and wood to about 1,700s. When we started to use steel, structural steel, to about 1,900. When we started to using reinforced concrete, so the discovery and application of new materials is the driving force behind the development of structural technologies. We believe that a kind of a new material will be the solution for the corrosion issue. Fiber reinforced polymer composites are a potential solution which formed by embedding long fibers in a rhizome matrix. This the long fibers and the rhizome matrix. Depending on the fiber material, we may have, for example, glass fiber, reinforced polymer composites, that is glass FRP, carbon fiber. So we have CFRP, carbon FRP, basalt FRP, etc. We may also change the rhizome material to fit the functional requirements. FRP composites are featured by their outstanding corrosion resistance in harsh environments like marine, chemical, and coastal areas. They are also very light in weight, but very strong in their strengths. So also a special feature is the long conductivity and the non-magnetic feature, suitable for a specialized application. For example, the MRI facilities. You may have heard about FRP or composites in your life or work. FRP is mostly used in the automatic industry, which accounts for over 40% of the total use. Besides, the market of FRP has been continuously increased over the years, implying that FRP is gradually working into our life. Some car components are made of FRP. and some structural components of airplane are also made of FRP to reduce the structural weight. Except for the above traditional use, here are two recent news about FRP. One is good news. Tesla developed a new model saying that it has higher rotating speed, therefore can produce higher torque. The idea is to use CFRP to wrap the motor nearby, increasing the strength of steel for sustaining a higher force during rotating, just like us to use CFRP or steel to confine the concrete. Later, we will talk about more about the mechanism. Another one is an accident. Ocean Gate submarine just crashed under the Atlantic Ocean last year. They used CFRP to wrap the submarine, but I think it cannot take advantage of the high tensile strength of CFRP because the submarine body mainly sustains compressive force when it was under the machine. So in our civil engineering industry, there are many two types of FRP products. The first is the strengthening of existing structures. For example, we can use carbon fiber fabric with resin to wrap cracked columns or beams. This can not only restore the load capacity of the structural member, but can also prevent the further corrosion of steel rebars inside the columns or the beams. So maybe you will question about the confinement or the strengthening effect of such a thin layer of FRP on the structural member. Here I have two videos to show the effect of FRP confinement. The left was a normal reinforced concrete column under simulated seismic loading. So concrete quickly spot off from the core. The other was wrapped with a layer of FRP material. It retained good structural integrity as well as load capacity, also sufficient ductility for a very long time under the simulated seismic loading. So this is because of the confinement induced by the CFRP or GFRP, the FRP layer on the column. So the second type of FRP products in our civil engineering is for new constructions. They have FRP bars, stirrups, tubes profiles, etc. Here's an example in Hong Kong. A whip wall in Lei Yumon uses FRP bars as the reinforcement of the concrete of the whip wall body. Actually, PolyU has done many years of research in FRP composites and new material hybrid structures. Professor Jing Guangtang of PolyU established a systematic theory for FRP strengthened RC structures, reinforced concrete structures, including constitutive models for confined concrete, for concrete to FRP interfacial bond, and also precise finite element models. And some new material hybrid structures. A typical one is the FRP concrete steel double skin tubular member. They have been used as the bridge piers in recent years, and we are considered to use them as wind turbine towers. Professor Tang's research outcomes have been adopted by some design guidelines or standards in many countries. So in recent years, Professor Yu Tao, this is Professor Yu Tao, and Professor Tang lead a world-leading research on sustainable marine infrastructure enabled by the innovative use of seawater, sea sand, concrete, and FRP. This could address two challenges of coastal and marine areas. For example, our Hong Kong. One is the shortage of fresh water and river sand in these areas. The other is the corrosion issue of steel. By utilizing FRP as a replacement of steel, and by using seawater and sea sand as a replacement of river sand and fresh water, we can effectively use our local natural resources. That is, they are the seawater and sea sand. So this research is from fundamental mechanisms of FRP, seawater, sea sand, and other materials to the development of innovative structural forms with these new materials, structural health monitoring technologies, deterioration mechanisms of structures and materials to field exposure testing in a real marine environment. Our group has placed over 5,000 of specimens in two marine exposure stations, and we finally completed many demonstration projects in Hong Kong and mainland China. For example, this is FRP SSC labs in Jiangsu province, and FRP SSC road slab, paving slab in Shating, Hong Kong, and some other applications. With the financial support of the theme-based research project, PolyU has also established an advanced laboratory in this field. We have systematic facilities covering advanced FRP manufacturing, mechanical property testing, durability testing. For example, FRP protrusion machine enables the development of new components fitting Hong Kong's domestic requirement. For example, a Lloyd's barrier, lightweight Lloyd's barrier replacement of the steel one, an FRP 3D printer. Also, the horizontal tensile test platform is currently the only available one in Hong Kong that fulfills ASTM standards for the testing of all size FRP bars and soil layers. During these years of research and application, we have realized the limitations of FRP. Here is a video showing the tensile test of steel rebar. So you may find that the elongation is very, very long. So the steel rebar is very ductile. The vertical axis is the stress, and the horizontal axis is the deformation. So a very long deformation for steel rebars. So another video is for the tensile test for FRP rebar. So it is quite brittle, right? So the ductility issue of FRP is far inferior to that of steel. Also, the elastic modulus of GFRP, as GFRP is the most commercially available one for the use in our civil engineering, because CFRP is quite expensive. So GFRP, the modulus is much lower than that of the steel one. So this means that we need to have different design methods for FRP reinforced concrete structures, and also the reinforcement ratio in volume of FRP bars will always be much larger than that of steel. So although we can see FRP structures or FRP reinforced concrete structures will have a much lower life cycle cost, but the the high initial cost of these FRP structures or FRP reinforced concrete structures still is a major concern for the decision makers today. So in marine and coastal environments, actually, we have some other candidates in addition to FRP materials, including epoxy-coated steel, stainless steel, galvanized steel. For example, the Hong Kong-Zhuhai-Macau Bridge uses over 8,000 tons of stainless steel rebars. Some other bridges in Hong Kong also use similar solutions. So it has been a common experience for structural or particle engineering engineers to use corrosion-resistant rebars to enhance structural durability of concrete structures in marine environments. However, all the existing technologies have certain limitations. For epoxy-coated steel rebars, the key drawback is, I think, is labor-consuming. As the epoxy coating layer is easily broken, epoxy-coated steel rebars need careful damage detection before the use and repairing when damage is detected, and careful handling during the operation process. But we all know that it is very difficult to meet all these strict operational rules because collision and impact are hard to be avoided on site. The key drawback of galvanized steel rebars, I think, is the insufficient durability because corrosion will happen after exposure to outdoor environments for just several weeks. The key drawback of stainless steel, I think, is the extremely high cost of it. It is about 5 times more expensive than that of normal steel rebars. For normal steel rebars today, about 5,000 Hong Kong dollars. For stainless steel rebars, it is about 30,000 Hong Kong dollars for stainless steel rebars. The key drawback of FRP rebars, I think, should be user-unfriendly because they have new material properties, new material constitutive models. So you need new structural design procedure and new handling rules for them to use. So as we just talked before. So against these limitations, Professor Tang and our group members invented a new type of corrosion-resistant steel rebar. We believe this can address these problems. Such rebars consist of a thin layer of FRP covered on the core steel rebar. So the FRP coating layer was made by the filament winding technique. The innovative use of filament winding technique with fibers. The fibers were close to the hoop direction of the rebar. Ensures that the FRP coating layer is in close contact with the substrate steel, and the geometry of the ribs of the rebar is largely retained for excellent bond with the surrounding concrete. So this is the concept of the rebar. Our group has developed 2 different manufacturing methods for different quality requirements. The main procedure will include pre-treatment of steel, filament winding of the FRP coating layer, curing and hardening of the coating, surface treatment. So here is a video showing the filament winding step. So from this video, you may find the coating layer is very thin on the steel. So the ribs were largely retained on the surface. So the bond with concrete is very good. To test the corrosion resistance of FRP coated steel rebars, we first placed some different kind of rebars in the outdoor environment in Hong Kong for 6 months. After the exposure, this is the bare steel rebar corroded, and the epoxy coated steel rebars corrosion mainly experienced at the edges of the ribs where the epoxy coating layer are very thin there. The FRP coated steel rebar remained uncorroded, unaffected by the atmospheric corrosion. So when we then placed the three types of rebars in sodium chloride solution as a simulation of the seawater for 12 months in the laboratory, the FRP coated steel rebar also remained a very good state, where the other two rebars corroded seriously. So these observations confirm that the FRP coated steel rebar has a superior corrosion resistance in the laboratory environment. So in addition to the laboratory exposure, we also placed some FRP coated steel rebars in a real marine environment just near Hong Kong. It is the west artificial island of the Hong Kong-Zhuhai-Macau Bridge. The exposure condition is the splash zone, which is a very harsh corrosive environment for metal as specified by the existing exposure standard. We designed a special fixture to apply a pre-tension to the FRP coated steel rebar. This is the FRP coated steel rebar, and also for the simulation of its real stress state in service. The top and the bottom, we call these profiles, were made of galvanized steel, and the two screws were made of stainless steel. So just for a quick comparison during the exposure. After 2 years of exposure in the marine environment, the galvanized steel corroded seriously, and stainless steel also exhibited pitting corrosion. But the FRP coated steel rebar was still in a very good state. Even we cut it to check the cross section. As mentioned before, coated steel rebars, including FRP coated steel rebar, epoxy coated steel rebar, and the other coated steel rebars, have to experience collision and impact during their transportation and handling. We perform the job weight impact tests in accordance with ASTM standard after the impact, as expected. Epoxy coated steel rebar have the coating layer peeled off, and a large area of the substrate was exposed because the FRP coating layer has several layers of fibers stacking by stacking. Only the most exterior surface was damaged, with other deeper layers remain still very well. So to prove that the FRP coating layer is the deeper layer remains very well, to prove this, we immersed the impact damaged specimen in sodium chloride solution and measured the corrosion rate up to 36 hours. We call this post-impact corrosion rate, because we think if the coating layer has been damaged, the corrosion rate will be very high, and it can reflect the state of the substrate steel. So this is the corrosion polarization resistance, and this figure, the figure B, is the corrosion rate. So from this figure, we can find the black line is the bare steel rebar. It is the control. So because the steel got direct contact with the saline solution, so the corrosion rate was very high for bare steel rebars and almost consistent. So for epoxy coated steel rebar, the blue line, just as we just said, the substrate steel was contacted with the saline solution. So initially very low, not very low, and then remained at a very high value of the corrosion rate. Means the steel was currently in the corrosion state. So, but for the red line, it is for FRP coated steel. So the corrosion rate is was several orders of magnitude lower than the values of epoxy coated steel rebar and bare steel rebar. So this can confirm that the coating layer had much fewer defects and damage. So in turn proves that the FRP coated steel rebar have a much stronger impact and appeal resistance than epoxy coated steel rebar, because the mechanism is easy to be understood, because the fibers inside the coating layer can serve as a reinforcement of the coating. So normally we can think the FRP coated steel rebar is a upgraded version or strengthened version of epoxy coated steel rebar. So another concern for coated steel rebar is the bond performance with concrete. I think this is the concern for most of our structural portable engineers, because this governs the performance of the structural members. For epoxy coated steel rebar, it is known that there is a reduction in the bond performance because of the existence of the epoxy coating layer. So we performed the pull-out test with reference to the ASTM standard and found that the local bond strength of epoxy coated steel rebar, this is the epoxy coated steel rebar, this is the bare steel rebar, so about 2% lower than that of bare steel rebar. So, but the FRP coated steel rebar had a bond strength much higher, even higher than that of bare steel rebar. So from the bond stress and slip curves, we can also from this chain, these two lines are for bare steel rebar and epoxy coated steel rebar, and the red line is for FRP coated steel rebar. For each line, it is an average of 3 samples. So for the reason, I think the partially because of the enlargement of the diameter by the FRP coating layer. Well, the local, because when we calculating the local bond stress based on the pull-out test results, we just use the normal diameter of the core steel rebar, not the overall diameter of the rebar. So because of these results, that means if we try to design a steel reinforced structure, concrete structure, we do not need to consider a reduction factor of the bond performance, because maybe if we use epoxy coated steel rebar, for example, when we're estimating the anchorage length of the rebar, we need to consider a reduction factor of the bond strength. That parameter is normally is smaller than 1.0. So that means we need longer anchorage lengths. So this is the bond performance with concrete. We then used 3 types of rebars to make concrete beams for flexural loading. This load displacement, this is the load displacement curves, are generally similar. We'll find that they are generally similar. But the ultimate load for the beam reinforced with FRP coated steel rebar was slightly higher than the other two beams, but generally very close. More importantly, I think from the crack patterns, we can find the crack number and the spacing, the crack spacing for the beam reinforced with FRP-coated steel rebar is generally the same as the beam reinforced with bare steel rebar. So, but for the epoxy-coated steel rebar, just as expected, the number of cracks was much lower than the other two beams, and the spacing of crack much larger than these two beams, and the crack width a little bit wider than the other two beams. So this first confirms that the previous slide, that the bond performance of FRP-coated steel rebar is much better than epoxy-coated steel rebar, and also confirm that the flexural performance of the beam reinforced with FRP-coated steel rebar have better flexural performance. So, in addition, FRP-coated steel rebars are highly cost-effective, as only a small amount of additional materials, for example, fibers, resin, are used. So, the unit cost, according to our current manufacturing method, is estimated to be only 1/4 of that of stainless steel. So currently, the bare steel rebar about 4,000 to 5,000 Hong Kong dollars. For galvanized steel rebar, also slightly higher than bare steel rebars. For epoxy coated steel rebar, normally 6,000 to 7,000, and for stainless steel, normally over 20,000 in Hong Kong, depending on the type of stainless steel you use for marine applications. We normally have a type that we call 316. So for that type of stainless steel, the cost will be normally 30,000 for that kind of stainless steel rebar. So for FRP coated steel rebar, we think the performance, this is the overall performance, including the bending, the corrosion resistance, the ductility, the overall performance, I think, is comparable to stainless steel, and the cost just within this range. So the cost effectiveness is very good. Besides, I think we just talk about the ductility issue of FRP rebars. So for FRP coated steel rebar, we think it is as ductile as the core steel rebar, because we just have a thin FRP coating layer covering the steel rebar, the core. So the fibers were largely deviated from the longitudinal direction because they are in the hoop direction, so contributed very little to the longitudinal behavior of the rebar. So the ductility of the FRP coated steel rebar, we think, is comparable to the original steel rebar. So don't worry about the ductility. So up to the present, FRP coated steel rebars have been used in we think three field applications. The first one is the we call door bars of the reinforced concrete base under corrosive FRP SCC pavement. This is in Hong Kong, in Shatin, and these slabs, we just talked about this, made with FRP and FRP rebars, reinforced seawater sea sand concrete. So under these slabs, we have reinforced concrete base. The reinforced concrete base composed of 3 large slabs. Between two slabs, we have some dowel bars to transfer the shear force. So initially, these dowel bars were designed with normal steel rod. So we made the FRP-coated bars to be used as the dowel bar. So in this project, we made about 8 bars with a length of half a meter, and the diameter for this dowel bar 32 millimeters. The second project is the reinforcement, longitudinal reinforcement of 4 beams of a FRP SSE mock-up frame. This is a part of the theme-based research project of our group. So each beam, these 4 short beams, each beam has 4 such rebars with a diameter of 16 millimeters, and the length is 1.6 meter. So we are monitoring the state of the rebars inside the frame. Currently, the frame is located near the sea beach. So this is the second project, and the beam is made of seawater and sea sand concrete, so it is corrosive. This project is in Zhuhai. There is a Guishan Island. So the most recent one is the longitudinal and transverse reinforcement of a 10-meter long weave wall in Leyumun in Hong Kong. So we manufactured various shapes of such rebars: straight one, U-shaped one, Z-shaped one, and L-shaped one. So this is the rebar cage of the weave wall, about 10 meter long. Currently, the project was completed, the concrete casting. So this is the concluding remarks today. So FRP-coated steel rebars are expected to offer a much cheaper alternative to stainless or FRP rebars as corrosion-resistant reinforcement for concrete structures in marine and other corrosive environments. FRP-coated steel rebars are superior to epoxy-coated steel rebars in terms of the impact and peel resistance, rebar to concrete bond, and also the corrosion resistance. So it is easy to replace steel rebars with FRP-coated steel rebar of the equivalent diameters in a project, as there is no special requirement to change the original structural design. So I would also like to acknowledge the financial support from the RGC Hong Kong, from PolyU, and also from Hong Kong STP. Apart from the works presented today were done by Dr. Yiwen Zhang, a former PhD student co-supervised by Professor Tang and me and Professor Yu Tao in her PhD research. So thank you for your attention. Just want to know if there is a question from you.
Thank you very much, Dr. Xiang. So right now we'll be taking in questions, and I can see that there are 5 questions in the chat box. Should I start reading them one by one?
Yes.
Okay. The first question would be, how does the bond strength of concrete with traditional steel bar compare to that with FRP-coated steel bar? I believe this question was...
So we just reply to the question one by one, or is that okay?
Yeah.
Okay. So for the first question is about the bond performance. So for the bond performance, we actually here we just present a brief comparison. Actually, we did a lot of experiments. So for a brief comparison, it is even better than bare steel rebar. That is the question. Traditional steel rebar, yes, it is even better because we think partially because of the enlarge the coating layer, enlarge the diameter. So, but actually, when we estimating the bond strength, we use the smaller one, that is the core diameter of the core steel. So this is because the reason, but at least they are comparable. So for the first question.
All right, thank you. The second question would be, if air bubbles present between FRP coating and steel rebar during wrapping, are they affecting the performance of the FRP coated steel bar? If yes, how to detect and how to avoid those air bubbles during manufacturing?
Yeah, for this question, a very good question. That is related to the we think is the production or manufacturing of the FRP-coated steel rebar. So here I just presented an SEM, a microscope image here. So for the dark part, it is the FRP. So this is the fiber, this is the resin, and this is the lighter one is the steel. So from this interface, we can the bubble was properly eliminated by the manufacturing methods we developed. We think we have 2 points to control the bubbles. The first is to control the tension of the fiber. So we have we designed the tension and to keep the close contact between the fiber and the core steel rebar. So the bubbles will be first eliminated or reduced. And second, we have other procedure to control the air bubble. For example, we use vacuum pressure to make them to be more closely contacted together. So I think this is about this question.
All right, thank you. The third question would be, can this coated steel rebar be bent at construction sites when FRP coating is exposed to water containing dissolved ions, such as alkalis present in cementitious materials? Would a high pH value degrade the fiber matrix?
Very good question. I think this question actually we have 2 points. One is about the on-site bending. So from this picture, you can find the curved shape we call U-shaped, Z-shaped, and L-shaped. So this is just the bend. But for currently we have 2 methods. One is for on-site bending. But if you use on-site bending, we must select we call thermoplastic resin so that we can achieve on-site bending by heating it and then bend it, so we can have the reshape. We call reshape the rebar on site. Another option is you give me the design and we bend it on in a laboratory or in future in a factory. So design the shape, bend it, and transport these rebars to the construction site. So the second is when the coating layer is exposed to water containing alkaline and other things. I think this is a good point. We are currently studying this, but as you know, the coating layer is not very thick. So I think this is the pH value will not just for the FRP-coated rebar, that will be a governing issue. Because the degradation will happen and the mechanical properties will be affected. So this is the issue we are currently considering. Thank you.
Okay, thank you. The next question would be, how is the fire resistance of the FRP-coated rebar comparing with simple steel rebar?
For this problem, also very good question. I think this is a good suggestion that we need to consider the fire resistance. Currently, we use this type of rebars in marine and coastal engineering. So for these application situations, fire accident will not easily happen in these situations. But for in the future, if we want to use these rebars in like building constructions, so we must focus on this. Thanks for this suggestion.
Okay, next, the question has been split into 3 questions. Shall we go through it one by one?
Okay.
Yeah, the first one is in practical use, large bend angles, 90 and 135 degrees, is applied on cross tile link and link. Can the coating in FCSR sustain large bending angle without undermining its corrosion protection ability?
Okay, so for the question, it is just that the large angle between a large angle were applied on the cross side or link. So this question is about the corrosion protection corrosion issue about these angles. So for this one, we think in this project we think it is not very no problem about the corners there because for this project we call this is wet bending. Wet bending. What does that mean? Because that is we apply the coating layer, and before the hardening, we do the bending. So and then we put these specimens or the rebars to into a environmental chamber to make it hardening. So for this coating angle, we think no problem. And besides, I need to explain one point. That is the fiber. So for these rebars, the fiber is mainly along the hoop direction. So when we do the bending, the separate just between the fibers, right? So this will not affect the coating rupture or break. So for the second question is, can FRP coating be applied to normal rebar on site? Yes. This is a problem also raised by some other on-site engineers there. For this project, we produce these rebars and transfer to the construction site. They think it is very the time consuming. So they just think about this. Sure, because the manufacturing facility is not very large. So if on-site rebars needs this FRP coating, so we can also do this on-site. For the second question, for the third question is other than applying FRP coating to the hoop and special treatment of both ends. For this both ends, currently we use a plastic cap between cap on the end of the FRP-coated steel rebar before applying the coating layer. Just like after the treatment of the steel rebar, descaling the oil, and then we apply the cap, and then we do the 1D. We do the filament 1D just by to make the FRP coating layer. So the two ends will be properly protected by the caps. So this is the question. This question.
All right, thank you. The next one is how to detect corrosion through electrochemical methods in such rebars when the epoxy itself is non-conductive. So the resistance may always be high, and you presented different shaped bars in project 3. Were those shapes prior to FRP coating, or you bent the rebars after coating the FRP?
Okay, so for you are talking about this slide. So for epoxy coated steel rebar, normally if the coating layer of a epoxy coated steel rebar is very well is in a very good state. So if you perform electrochemical test, you actually the long conductive, it is non-conductive. So for this test, we just first apply a impact to destroy the coating layer, and then we to simulate the possible collision or impact during the operation process or the construction process. So and then we do the electrochemical measurement. So in that way, we can measure the corrosion rate. So maybe you will ask, you will ask how to compare if all these rebars were in very good state. Actually, that is very difficult. That is very difficult. But the actual situation for in our on-site construction is the epoxy coated steel rebar indeed has many defects on the coating layer. So we think the measurement can reflect the real situation. The second part of this question is in project 3, where this project shape prior to FRP coating or bend rebar after coating with. For Z shape and L shape, in this project we tried 2 methods. For these two, Z shape and L shape, we bend them prior to making the FRP coating. For U shape, as requested by the contractor there, we do the bending after making the coating with the FRP. So in a hardened state. So for this one, we applied an additional layer of coating after doing the bending, because we realized if we bend it after hardening of the coating layer, there will have many cracks on it. So we applied an additional layer. Maybe from this figure you can see the additional coating layer on it. So in two situations, I think this is the answer for Das question.
All right, thank you. The final question would be, is the FRP coating technology also applicable to steel H or I section?
Actually, I think some of my group members, they are trying to applying the FRP coating technology to other shapes of steel profiles, just like H shape or I shape. But the problem is, this is for the shape. You from this figure you will find that if we want to do the filament winding, if this is inward, there is an inward shape at the profile, so it will be very hard to make the coating layer properly fitting the shape of the profile. So so my answer is yes, applicable, but you have difficulty in achieving the same effect of the FRP coating. Thank you.
All right. So are there any more questions coming in? Oh, there's one more question. FRP coating is applied for steel rebars by wrapping instead of hearing or chemical treatment. How to ensure the coating sticking on the steel bars?
Yeah. Here I just for the manufacturing of one steel rebar, actually we have many steps. From the first step, that is the pre-treatment of the core steel rebar, like the oil, the descaling. Okay, so heating. Oh, you mean how to make the coating layer to be hardened, right? So for the because we want to reduce the energy consumption. So for this technology, we do not need to use additional heating or other. Just put them in a room temperature for several hours, and then it will harden.
All right, thank you. I guess we are right on time. So thank you very much again, Dr. Xiang. So looking forward to seeing everyone else in other webinars. Thank you so much. Have a good evening.
Thank you. Thank you so much. Thank you, Christy. And thank you for the all